Let's say we want to solve a quadratic equation. X squared plus 2x plus 4 equals 0. Now, if we use the quadratic formula, x equals minus b plus or minus the square root of b squared minus 4 times a times c, all over 2a. Simplifying that, we get minus 2 plus or minus the square root of minus 12 all over 2. But we've got a surd there. Let's simplify that surd. So we end up with 4 times minus 3 under the square root sign over 2. Take the square root of 4 out the front so it becomes a 2. And then divide everything throughout by 2. So you've got minus 1 plus or minus the square root of minus 3. But the square root of minus 3 is the problem. So, looking at the quadratic equation again, if the roots exist, we know that the sum of the roots, alpha and beta, have to be minus b on a, so that's minus 2, and the product of the roots have to be c on a, so that's 4. So, if they exist, then we should get some roots. So, looking again at what our answer was, x equals minus 1 plus or minus the square root of minus 3. Now, let's split the minus 3 and make it 3 times minus 1. Because it's a surd, using the surd rules, I can have the square root of 3 times the square root of minus 1. Now that the square root of minus 1, that's the problem. So what if we let something else be the square root of minus 1? So let's start by letting I squared equal minus 1. If that's the case, then I would equal the square root of minus 1. So we will have x equals minus 1 plus or minus root 3i. So the two solutions are x equals minus 1 plus root 3i and minus 1 minus root 3i. So do the sum and the product of the roots work? Okay, remembering x equals minus 1 plus root 3i and minus 1 minus root 3i. If I add the two roots together, it's like going minus 1 plus root 3i minus 1 minus root 3i. Just like algebra, the plus root 3i and the minus root 3i cancel, and we're left with minus 2, which is what the sum of the roots should be. The product of the roots, minus 1 plus root 3i times minus 1 minus root 3i. 1 times 1 is plus 1. Then the outer 2, we get plus root 3i. The inner 2, minus root 3i. And the last two multiplied together, we get minus root 3i times root 3i. So we get 1 plus minus, they disappear. Minus root 3 times root 3 is 3, and then I squared. But remember from before, we let I squared be minus 1. So I times that by minus 1, 1 plus 3, which equals 4, which is the product of the roots. So by letting I squared equal minus 1, that allowed us to solve that quadratic equation, which ordinarily in the real number system doesn't have any solutions, but in the complex system it does. Having a look at our number line, if I want to go from 1 around to minus 1, that's the same as multiplying by minus 1. And then if I go from minus 1 back around to 1, that's by timesing by minus 1 again. Or if you like, getting from 3 around to minus 3, we can times by minus 1. And then from minus 3 all the way around to 3, we're also timesing by minus 1. And remembering, we let I squared equal minus 1. So if I wanted to go from 1 to minus 1 all the way back around to 1 again, I'm really timesing that by I to the 4th. And that gets us back to the original place. So timesing by I squared is like a rotation of 180 degrees, or pi radians, and then when I multiply by I squared again, it's bringing it back to the original position. So timesing by I squared is the same as a rotation about 0 in an anti-clockwise direction of pi radians. So if I start from 1 and I make it all the way around there to minus 1 by multiplying by I squared, what happens if I only went to there? It's actually like timesing it by I. Then from there to there, timesing it by another I, and another I. So timesing it by I to the 4th gets it back to the original position. So if you just want to times it by I, it's like a rotation about 0 in an anti-clockwise direction by pi on 2 radians. And in the complex system, we call this horizontal axis the real axis, and the vertical one the imaginary axis. And on the imaginary axis here, we call that I, if it's 1 unit up the vertical axis, and this one down here is minus I. So if I have I to the 1, that just equals I squared, remembering we go from 1 all the way around to minus 1. If I have I cubed, that will take me around here down to minus I, and then if I have I to the 4th, that will take me back to my original position. I can keep going around this unit circle. I to the 5th would be I to the 6th would be minus 1, and so on. The number plane of real and imaginary numbers is called the complex plane, or an Argand diagram. And a complex number has two parts to it. We'll call the complex system Z. It has a real part and an imaginary part. So A and B here are real numbers, and Z equals A plus IB. Or if you want, Z equals X plus IY. Doesn't really matter what we call those variables. So an example of a complex number could be something like 1 plus 2i, or 3 minus 4i, or minus 7 plus 3i. They are all examples of complex numbers. If we just have a, it's actually a real number because there is no imaginary part. If we have something like that, it's completely imaginary because it's got no real part. And if we have an a plus ib, as long as a and b aren't 0, then that is a complex number. The complex number system, as we just said, deals with real numbers and imaginary numbers. Imaginary numbers we just call M, and real numbers we call R. So this is the complex system which encompasses both of those. But within the real system, we have the rational numbers, which we can denote with a Q, and then inside that we also have integers, which we can use as Z to denote. Okay, so complex numbers consist of a real part and an imaginary part. Just like with the real number system, we can do operations on complex numbers. So if I've got two complex numbers, Z1, which equals 3 plus I, and Z2, which equals minus 2 plus 5I, I can add them, where I just add the real parts together. So 3 plus minus 2 is it's plus 1, and plus I plus 5I is plus 6I. I can subtract them. So once again, the real part, 3 take away minus 2 is 5, and then plus I minus 5i is minus 4i. I can even multiply them. So if I have 4 lots of Z1, I just want 4 lots of everything that's in Z1. So 4 3s are 12, and then 4 lots of I, which is 4i. I can also multiply Z2, say, by 5i, which means I multiply everything that's in Z2 by 5i. If I do that, 5i times minus 2 is minus 10i, then 5i times 5i. 5 times 5 is 25, but I times I squared is minus 1, so that becomes minus 25. And convention says we do the real part first, followed by the imaginary part. We can even multiply two complex numbers together. If I've got Z1 times Z2, multiplying those two together. So we have the first two multiplied together, minus 6. The outer two gives you 15i, the inner two minus 2i, and the last two plus 5i squared. So minus 6, 15i minus 2i is 13i, but the I squared is minus 1, so that becomes minus 5. So the real part is minus 11, and then we're left with plus 13i. Another thing we have is just like what we have with surds. If I've got z plus ib, and that's a complex number, then the complex conjugate, which we call z bar, is a minus ib. So we call that z bar. And if I want to multiply z by z bar, so multiplying a plus ib by a minus ib, if I multiply the first two, I get a squared. The outer two and the inner two will cancel, and then I'm left with plus ib times minus ib, which will equal a squared plus b squared. So if I am multiplying z by its conjugate, z times z bar, I will end up with a squared plus b squared, which is real. So for example, if I let z equal 3 plus 5i, then z bar is going to be 3 minus 5i. If I multiply z by z bar, that's a, that's b, so a squared plus b squared, which equals 9 plus 25, which is 34, which is a real number.